Make triangles from random side lengths, and one shape keeps piling up, the equilateral triangle. Here are 50,000 of them, sorted by their first two angles. The bright mound is centered at 60 degrees, which forces the third angle to be 60 as well. That is already suspicious. We never asked for symmetry. We just picked three positive numbers at random, kept the triples that could close into triangles, and measured their angles. Scaling triangles vastly outnumber perfectly equilateral ones, of course. In fact, the chance of hitting one exact shape is 0. And yet, when we group nearby shapes together, the equilateral neighborhood wins. So what is doing the grouping? My first guess was the triangle inequality. It rejects the absurd triples like two tiny sides and one enormous side, so maybe that rejection simply herds everything toward equality. Reasonable. Also incomplete. Because if we plot the accepted side lengths after dividing each by the perimeter, there is no mound at all. The points spread perfectly evenly across a flat triangular region. Same random triangles. Flat in one picture, sharply peaked in another. That is the actual puzzle. Nothing about the triangles changed. Only the coordinates did. So before we explain why 60 degrees becomes the favorite, we need to catch a quieter trick. What exactly does it mean to choose a triangle at random? The phrase random triangle is hiding the whole machine. Pick 3 random points in a square, and you get one distribution. Break a stick twice, and you get another. Pick 3 angles, or 3 sides, or 3 vertices on a circle. Different again. There is no universal urn containing every triangle once. For this experiment, we will use a rule that is unusually clean. Choose 3 independent positive numbers from an exponential distribution. Call them x, y, and z. Then divide each one by their sum. Now a, b, and c add to 1, so they describe side lengths as fractions of the perimeter. The useful miracle is that the normalized point lands uniformly on the entire simplex, the filled triangle of all positive triples satisfying a plus b plus c equals 1. Every equal area patch is equally likely. But most of that simplex does not make a geometric triangle. If a is at least 1/2, then a is at least b plus c, and the other two sides cannot reach each other. The same goes for b and c. Cutting away those 3 impossible corners leaves the smaller inverted triangle in the middle. And because we started uniformly, conditioning on survival leaves this middle region uniform too, no preference. The center, where all 3 sides equal 1/3, is no denser than a patch near an edge, so the triangle inequality does remove extreme shapes, but it does not produce the mound we saw. That guess is dead. The mound appears only when these evenly scattered side triples are translated into angles. Somehow, equal steps in side space become unequal steps in angle space. How? Take 2 equal little squares in that side length region. Since the sampling is uniform, they receive the same number of triangles. Now send both squares through the law of cosines. The square near the center becomes a surprisingly small patch in angle space. The square near a nearly flat triangle stretches into a long, thin patch. Same probability, very different area. That is the squeeze. If 100 samples are packed into a small angle patch, the angle histogram looks dense there. Spread the same 100 across a large patch, and it looks sparse. The equilateral shape is not attracting triangles. Our angle coordinates are compressing the side space around it. You can see the compression with one motion. Start with an equilateral triangle and increase side a slightly while decreasing b slightly, keeping the perimeter fixed. The angles change, but gently. Now perform the same side-side adjustment on a triangle that is almost flat. One angle swings violently while another nearly collapses. Near the boundary, tiny side changes create huge angle changes. So, uniform side uncertainty becomes enormous, angular uncertainty there. At the center, the same uncertainty barely moves the angles, and many nearby side triples land in one angular bin. This is the same reason a world map can make Greenland look gigantic. A map is not merely relabeling points, it stretches some neighborhoods and squeezes others. Here, our map is from normalized side lengths to angle pairs. Fine, but we can do better than a map analogy. We can calculate the exact local squeeze, and it comes from a very old fact about triangles. Their sides are proportional to the sines of their opposite angles. If a triangle has angles at b and c, the sine rule says its sides have the ratio sine a to sine b to sine c. Since our perimeter is 1, the actual normalized sides are equal sine, divided by the sum of all 3 sides, and similarly for b and c. Also, c is pi minus a minus b, so 2 angles determine everything. This gives us a machine. Move a point in the angle triangle, feed its angles through 3 sine curves, then normalize the outputs into side lengths. What matters is how much area the machine creates or destroys locally. That factor is a Jacobian. The name is less important than the job. Draw a microscopic square in angle space, map its 4 corners into side space, and measure the resulting area. Work through the derivatives, and the area factor is proportional to sine times sine b times sine c, divided by the cube of sine a plus sine b plus sine c. That expression is the density of our random triangles when plotted by A and B, apart from one overall constant. Now look at its behavior. If any angle approaches 0, one sine approaches 0, and the density dies at the boundary. Near a flat triangle, angle space expands so aggressively that each little angular patch receives almost no probability. At 60, 60, 60, all three factors are balanced. The product is large, the denominator does not rescue any lopsided competitor, and the density reaches its maximum. There it is. The favorite shape is the point where the side-to-angle map performs its strongest local compression. Not a force, not a hidden bias in the random number generator. Geometry changing the size of neighborhoods. That formula should predict more than one attractive picture. Let's try to break it. We generate 200,000 normalized triples, discard the ones outside the triangle inequality, convert every survivor to angles, and compare the histogram with the formula. The slices line up, low near 0 degrees, rising toward the middle, then falling as the third angle is squeezed out. Good. Now tighten the circular window around 60, 60, 60, and compare it with equal area windows elsewhere. The equilateral window wins, just as the Jacobian predicts. But here is a consequence I did not expect from the phrase, favorite shape. The typical triangle is not especially close to equilateral. The peak tells us where the density is highest at one point. It does not tell us where most of the total probability lives. A narrow mountain can lose to a broad plain. There is much more angle space available away from the exact center, so a randomly selected triangle is almost certainly scaling, often noticeably so. This distinction matters everywhere in continuous probability. The most likely exact height of a person, measured with infinite precision, has probability 0. A density peak only says that equally small measurement bins near that value beat equally small bins elsewhere. Make the bins uneven, or describe the same objects with different coordinates, and the winner can move. So when we call equilateral the favorite, we mean something precise and limited, under uniform normalized side lengths, and using equal area bins in two-angle space, the probability density is maximal at the equilateral point. That sentence is less magical. It is also the version that survives contact with the experiment, but now we've created a slightly ridiculous problem. If changing coordinates can create a favorite shape, can we choose coordinates that erase it again? Yes. In the normalized side coordinates we started with, the distribution is flat, so every equal area neighborhood ties, no favorite at all. We can go further. Warp the coordinates deliberately, and almost any ordinary shape can be made to sit under the tallest density peak. That sounds like probability has become arbitrary, but the probabilities of actual sets never changed. Pick a concrete collection, say, all triangles with every angle between 50 and 70 degrees. Whether we describe those triangles by sides, angles, or some warped pair of numbers, the chance of landing in that collection is identical. What changes is the drawn area of the collection, and density is probability divided by that coordinate area. Shrink its picture, density rises. Stretch its picture, density falls. This is the consequential caveat. A mode is not coordinate invariant. The equilateral peak is real in the angle chart, useful, measurable, and still not an intrinsic crown worn by the triangle itself. Is there a description of shape that does not depend on our choice of axes? We need to decide what counts as equal separation between two shapes. Imagine deforming one normalized triangle into another, and measuring the amount of change. Different distance rules give different area elements, hence different notions of uniform randomness. Shape statistics often handles this by representing a triangle through its vertices, removing translation, scale, and rotation, and placing the remaining shapes on a curved shape space. But even then, the sampling mechanism matters. 3 Gaussian points in the plane, 3 points in a disk, and 3 broken stick lengths induce different distributions on that space. Randomness belongs to a procedure. It never belonged to the noun triangle by itself. So the opening mound was neither an illusion nor a universal law. It was evidence of our particular experiment. We chose side proportions uniformly from the region allowed by the triangle inequality. In those coordinates, nothing was preferred. Then we asked for angles. The sine rule folded side space into angle, space with unequal local magnification, enormous near flat triangles, smallest at the balanced center. Equal side space area therefore crowded most tightly around 60, 60, 60. That is why the angle histogram grows an equilateral peak, and this gives us a useful way to read any random shape claim. First, find the generator. What physical or mathematical procedure produced the samples? Second, find the coordinates. Are we counting equal intervals of sides, angles, vertex positions, area, or something else? Third, distinguish a density peak from a typical sample or a high probability region. Those are 3 different questions, and plots are quite happy to make them look like one. Return to the original 50,000 triangles. The central glow now means something much more specific. It does not say nature secretly wants equilateral triangles. It says that near the equilateral shape, many equally likely side-length neighborhoods are squeezed into a small angular neighborhood. The peak is a footprint of the coordinate transformation. I like that more than the mystical version, honestly. Randomness did not discover a favorite triangle. We changed rulers, and the geometry showed us exactly where the new ruler bunches up.